separate topic, which is essentially, sort of, we are kind of broadening our scope. Until now, we looked at links between pages. So it's like pages have friends. They are talking to each other by putting links to each other. Okay? And in fact, when we decided what is a good page, what's the important page, what's the less important page, it was essentially as if pages are defining among themselves a network, a social network. Okay? And we are sort of using social network analysis in computing page rank and authorities hubs. What I want to do now is take a step back and actually look at social networks, which is the traditional area that gives the theory to this link analysis. Just as traditional IR gave the theory to web-based IR. Social network gives you the theory for link-based analysis. So we'll take a step back and look at social networks. And even as we're discussing this, we will have insights about what we just completed doing. Okay. So that's basically the point. Okay. So social networks are pretty important. Just as information retrieval is important, even if you didn't have web. And social networks are important, even if you didn't have web. But they became even more important because of the web. Okay. So it's actually. So we will be focusing more on the web applications, but when understanding the background, you'll probably look at more than just web. Okay, so here are actually some examples of networks, and it's kind of an interesting thing that I put together mostly because they're like across the board. This was Typhoid Mary. How many of you know about Typhoid Mary?
Isn't that Mary Q?
No, that is Radiation Mary. Typhoid Mary was essentially this lady who, I don't know where it was when there was a big epidemic of typhoid. She was one person who wasn't getting typhoid. She was only giving it to people. She had the ability to resist the typhoid virus. Okay, so she was a great vector, and she actually used to run, I think, some sort of a hotel. And so, people were getting typhoid from her, and she herself was fine. And they actually, when these kinds of epidemics start, and you're trying to figure out where is the epidemic coming, you need to do social network analysis. Who did you talk to? Who did you talk to? And who are you hanging around with? And who are they hanging around with? Who are they hanging around with? Until you find the person who doesn't seem to be getting affected. In this particular case, this was pre-Bill of Rights era, presumably, and they just said, Typhoid Mary, you get to stay in the hospital forever. And she was essentially put in the hospital, and she was quarantined for not having typhoid. Okay, this is interesting. Did you understand what I'm saying? Because she doesn't have the symptoms. She has the virus, but she doesn't have the symptoms. What that means is she can keep giving it to other people.
Isn't it easy to just cure her and send her?
What?
Isn't it easy to just check her periodically? Okay, sorry.
Don't ask me the social policy. Okay, that's Typhoid Mary. Okay, her name is Mary Malan, and it's a very interesting story. You can do Wikipedia and all of this. Okay, this is modern day, not Typhoid Mary, but in fact, again, an epidemic analysis, not particularly modern because you're still probably born on a day before yesterday. This is patient 0, Gaetan Dugas. Who knows who that person is? Gaetan Dugas is a Canadian airline steward who essentially has been, statistically shown to be the first person to get HIV/AIDS virus into North America. Okay, so again, they were trying to figure out. Remember, for the longest time, it's so easy for us to make fun of our ancestors. Like our ancestors were such bozos that they used to think that the earth is in the middle, everything was revolving around. We are just as much of a bozos, because when the AIDS epidemic hit, pretty much anything would be seen as an explanation for who will get AIDS. For a while, by the way, they found that Haitians, people from Haiti, happened to have AIDS. And so they decided Haitians should be shunned. And that was as if Haiti doesn't have enough problems of its own. For a while, Haiti was shunned just because there were people from Haiti who had AIDS, as if just the country makes you get AIDS. Okay? And then after a while, we said, no, homosexuality makes you get AIDS. And in this particular case, actually, this guy happened to be a gay Canadian air steward. And so that was easy to say. That is, but Canadians, and of course Canadians get mad at us if we say they are the people causing trouble. So we'll say whatever else you can easily say is the reason. And then of course, just as Typhoid Mary was confined to hospitals, we can find a bunch of homosexuals to various hospitals for a while. That's what, as far as this particular course is concerned, social network analysis on AIDS epidemic. Okay, this is actually an interesting question. One time I asked you, what is the probability that if you take 2 random pages on the web, and if you just start from the page 1 and follow links, you will get to the second page eventually. What's the probability that if I give you 2 random pages, one is always reachable from the other? I asked you this question previously, and you didn't quite, obviously nobody knows the answer. To actually answer that question, you need to understand the topology of the network on the web. Okay? The last time around somebody did a good analysis of the topology of the web, which is unfortunately already old. This is like I think 7-8 years old. One of the interesting things they found is that web has this bow tie structure. Okay? Does this look like bow tie to you guys? I mean, of course, frayed bow tie with all these other things going around, but it's a bow tie, all right. Okay. So the point is, there is a big piece of 44 million pages. You can actually add up these numbers and see that this is old web. Right? It's not adding up to 8 billion. Okay. So about 44 million pages are essentially pages which barely have any links pointing to them. They're only pointing to other pages. That's your pages and my pages. Right? We just point to other people, nobody's pointing to us. And then there are Bill Gates of the world who do not beam down to point to you. They put up a page and everybody points to them, saying, my God, this is Bill Gates, this is Steve Jobs, etc. So there is also corporate entities where you will be showing links to those pages, but they would barely ever point to you back. Okay. In particular, actually, and then there is a central core where people are pointing to each other. The pages are pointing to each other. Okay. So these are the numbers, 44, 56, 44, and on all these funny things together are about 44 million pages. Now, if you know this, and now if I ask you, what's the probability that any 2 randomly selected pages would be reachable, one would be reachable from the other? You can answer this question. Right? If as long as one of the pages are between this plus this, the other of the pages are between this plus this, they would be reachable. Okay. Now, when you're thinking about this, actually, the question is, one is reachability. The other question would be approximately how many skips do you have, how many links do you have to follow to reach the other page? Okay. This is, of course, the 6 degrees of separation. I mean, there is this whole entire, point that any 2 random people in the world are connected with just about 6 people in between. So you know this person knows this person knows this person, and the last 6th person knows that last guy. Okay. Now, that idea that things tend to be connected more than you expect them to be has been called what? When you find some random person on the flight and you start talking and you suddenly find that you do have common friends after all, what do you say? You say, oh, it's a small world after all. So that's called small world phenomenon. Okay? So that basically 2 random entities have just a small number of links separating them. It's called the small world phenomenon. And one of the interesting questions in network theory is, for what kind of networks can you be sure that small world phenomena can be proved, it will hold? Okay, and in fact today or by the beginning of next class, we will see that random networks actually, surprisingly enough, are very highly likely to have small world phenomena. Okay, so you should not be surprised at all. You would only be surprised because you didn't know the theory of random networks. Okay, so in fact, one interesting question is that this sort of an analysis shows that the social network of web does have small world phenomena. And that will also make us wonder, since we happen to know that random networks, we will show that random networks have small world phenomena. And we know that web has small world phenomena. Can we then say web is a random network? Turns out you can't. Okay, and we will actually, that will bring us to the idea of power law networks, which is what web really is more like. We will understand the notion of power laws, the ideas of power law networks, and then point out that they too will have small world phenomena, except the difference between the power law networks on one hand and random networks on the other is, they have some very interesting differences. One of which, for example, is random networks are more affected by random perturbations to the network. So if in fact, consider a different network, which is the network of internet connections in between points in the web and the world. Okay? Now I'm trying to bring the internet in US down. Okay? When would it be easier? Would it be easier if the internet actually is a random network, or would it be easier if it's a power law network? It turns out that for random perturbations, power law networks are much more robust than random networks. Okay? Whereas for adversarial perturbations, that means somebody is out to get you, they can get you more easily if you have a power law network than random network. The whole idea is, how many times has anybody tried to do a denial of service attack on your page? Why not? Because you are not worth it. You're not important enough. You're not a big enough authority, you're not big enough node, you're not a big enough authority or a hub, so nobody wants to waste their time trying to do a denial of service on you. On the other hand, White House, I'm sure, all the days. Google, of course. Okay? And one of the interesting things we'll notice is in our discussion on social networks is this notion of power law versus random networks, and actually understand the differences. Even though they both will have small world phenomena, they also have lots of differences in terms of their robustness versus their ability to handle perturbations. Okay. By the way, actually, if you are into that, we will get to it in this class too, but there is actually a talk that has been mentioned in, somebody is giving a talk either today or tomorrow on robustness of networks. And you can actually go and listen to it, it's in 210. Once I go back, I'll send you a mail. Okay, and then this one is the last one, and this, obviously, this is the Florida 2000 ballot, which for some reason Bush won, and then somebody essentially who didn't like, I guess, Bush said, this is how the official Florida ballot looked like. Actually, official Florida ballot, how many of you know how again, the problem with teaching you guys is, I don't know when you were born, many of you were born last month, but if you were around in 2000, Florida ballot was what's called a butterfly ballot. What you have are circles like this, and then you would say Bush, Gore, Pat, what's his name? Okay, and the Bush like this. Okay, Pat this way, Gore that way. So you want to vote for Gore, you are supposed to vote to the third point. Okay. Florida, especially, I think the Broward County or whichever, which is like huge number of senior citizens who could barely see the names and definitely couldn't see the arrows, thought, okay, Gore is number 2, so I will click the number 2. And suddenly, what's his name? Pat Buchanan thought he was way more popular than he ever expected. That he never realized that he had so many fans in Florida. Because he was winning like crazy, because people basically thought number 2 would go to Gore, but number 2 went to Pat. And it was written. What's the most interesting, ironic things about it is, do you know who designed the butterfly ballot?
Bush's?
No, no. It was a Democrat who designed the butterfly ballot. Okay. And then, of course, when things went wrong, then they realized, man, we have low IQ people here, But that's a different story. So anyway, so when it's a Democrat who designed butterfly ballot, and then, of course, there was this whole jokes about how it was hard to figure out where to put goal. Okay, so there were all sorts of things, jokes, and one of which, and that is this guy, Mike Collins, apparently drew this cartoon. Okay, basically Bush goes like this, and what's wrong? What's hard about it? Buchanan, this one. So you just have to figure that out. Okay, so he made this cartoon, sent it to a couple of his friends. This was, remember, 2000. Web, as we know, has been going exponentially, big. Social networks more or less didn't exist. He sent it to a couple of friends and went home to, like a vacation. And when he came back, he found himself on CNN. Why? Because his friends sent to their friends, who sent to their friends, who sent to their friends, and suddenly it was like a viral, what we call now the viral phenomenon. Okay, which never was used that much at that time. And in fact, it's interesting to figure out what things would go viral, what things would not go viral, and how do you send ideas such that they will go viral. So for example, you give an idea to a sync node who doesn't talk to anybody, it's not going to go viral anywhere, right? So that's the other connection. So in fact, you can understand why things go viral, you need to understand social networks. Okay, so those are some reasons, we'll be reading it. But here are actually two more recent reasons for social networks with respect to this course. This one, they were essentially pointing out just last week that Saddam Hussein, they finally figured out where he was because they had all the time in the world, right? So they found out where he was by just drawing his social network on a big piece of paper. This is why we want dictators now onwards to have Facebook accounts. so that we can figure out who they are really friends to, so you can go talk to them. But essentially, at least this was a piece of the social network that they drew on a piece of paper. I'm sure somebody got a big DARPA grant for this, to draw this. And then they used that to figure out, let's just flush him out from one after other, because after all we do have $5 billion just for this. So we did catch finally. Okay, so that's Saddam Hussein's social network analysis. And you can imagine why DARPA and military is extremely interested in anybody who says they maybe thinking of figuring out what social networks do. Okay, because it's a very useful thing. You can catch Saddam Hussein. And then this is way more interesting actually from this course point of view. How many of you know about this news? Aardvark. You look like you knew, but you didn't. Aardvark, two people, okay? You all will know because I'll actually make you read the paper on Aardvark. This is a good way. So there is this joke about professors. A professor was dreaming one day, and then his dream, he says that, Professor Rao, your NSF proposal is so good that not only did we decide to double your funding, but also make a journal special issue where your proposal will be just published. And then we will also give you Turing Award. So cut the whole thing through. It's not money anymore. I just write one proposal, everything gets done. These guys did that. So what they did was they used to be in Google. Kamwar and what's his name? Max and but there's a guy called Sakwinder Kamwar and somebody else who originally were in Google, left Google, started this company, wrote a paper. It's coming out in 2010. Which you will get to read, okay? And also got acquired by Google for 50 million. 50 million is loose change in Google, right? If you're not sure, you would walk over it. So they gave them 50 million and took their company. They wrote a paper, got 50 million. That's as good as it gets, okay? It's actually what their point is that in normal life, if you want something done, you won't just search the web. Like for example, when I had to get my, my home repairs done, I wasn't just going to search the web to see who is a reasonable repair person. I would ask somebody I know, who did you get it done with? And then just go with them. So the question is, sometimes what you're looking for are other people who have, in your social circle, who have answers to your question. Okay, now the one interesting point about social networks is the friends in your social network may or may not share your interest in music, because I'm sure you have friends whose interest in music you don't like. You have friends whose interest in university major you don't like. The only thing you can say about your social network, hopefully, is that if they have an answer to your question, they're probably willing to think about your question and give you the answer. So they will give you the time of the day. Okay? But rather than ask the entire world, I have a question, please answer. Okay? It might be much more useful to see among my social circle or a couple of links away from my social circle, are there people who would be able to answer my question? In the old days, to answer this, you just have to go asking your friends, call each of your friends, hey, do you know I'm looking for a job? Do you know any jobs in your area? Do you know any jobs in Portland? And they say, no, I don't know any jobs in Portland, but I know this guy who is in Intel. Intel has a Portland facility, so I'll give you his number. And so you call this person and they will then talk to you about Portland. This is how normal, real social networks work. And they're very inefficient because you have to make calls. Most of us no longer have phones. What happens when you have the social network online is it's basically a graph search and a big graph, which is directly in front of you. Okay, so you may not know who is whose friend in Facebook. Other than your own friends, you don't know who is whose friend. Facebook very well knows who is whose friend. They not only know that, they know who are all the people 3 links away from you. They know this. So they can actually, if you are looking for jobs and you are trying to say, I'm searching for information about Portland Intel, they can tell you which of the people, what are the top K people who are either in your social network or like 1 or 2 links away from your social network, who are probably likely to answer this question. To do that, they have to be in your social network and they have to know the answer to this question. That's what Aardvark was trying to do. Okay, and you'll get to read this paper, but in fact, when you read this, you'll realize once again that, remember, what is the second best way of doing anything in this area? TF-IDF. And so they use TF-IDF. Okay, in fact, one way you figure out whether or not somebody might have an answer to your question, there are 2 issues. One is, are they in your social network? You follow the links, and Facebook can follow the links. The other is, if you have a question, how do you know that somebody might know the answer to this? Either A, they have already put a profile and so you find the similarity between your question and their profile. Or B, you look at all, make the profile by looking at all the pieces of text on their pages. And then compare the similarity between this query and their pages. Okay, now this is completely about finding not the best page, but the best person who will answer the query. Okay, and this is all the rage right now because I think Google, less than a week after they have acquired Aardvark, they already started saying now we will support social search. Only if you actually get onto Buzz, because you have to get out of Facebook and get onto Buzz so that they have access to your social network. And then they can answer their questions as to who might be able to answer your questions. Okay, so those are some of the reasons apart from link analysis that you would be interested in looking at social networks. Along motivation. So, there are tons of applications of network theory, some of which we just already mentioned, of course, World Wide Web and hyperlink structure, internet and router connectivity, whether or not a particular network structure is robust to attack with respect to attacks or not, collaborations among movie actors, scientists, mathematicians to figure out who knows who is the best scientist of them all, who is the most central scientist of them all, who is the most central Hollywood actor of them all. Who is the most central Hollywood actor of them all?
Kevin Bacon.
Kevin Bacon. Except it's not Kevin Bacon, we'll see in a minute. Okay? So Bacon turns out to be less central than some guy, called Rod Steiger, who actually has more centrality than Kevin Bacon. So, you can talk about those things, you can talk about sexual interactions. What's this? I mean, there are these very happy messages that people have been putting to stop spread of STDs and, HIV things and so on, saying, the person you are sleeping with, you are not just sleeping with them, but you have slept with everybody. And then there will be like a huge number of people, you have slept with them all. And then makes, I guess, different people will take that as a good or bad thing. But, again, the point is, the entire social network is now sleeping with you because they have slept with you. The network in this particular case is sexual interaction. Okay? Cellular networks in biology, food webs, phone call patterns, word co-occurrences in text. That's an interesting thing. It turns out that the way words occur together is implicitly defining a social network. And in fact, one of the things we will get to, apart from power laws, is when we are talking about power laws, we will talk about something called Zipf's law, which is the way words in a language are distributed in corpuses. Okay, not all words are created equal. Suppose I were to tell you that the most common word in English language is the, and in my corpus it occurs 19,000 times, let's say, maybe 20,000 times. Okay. Now, if I were to tell you the second most popular word in English language is let's say. How much do you think would be the number of occurrences of in my corpus? What is the frequency of the second most popular word given you know the frequency of the first most popular word? The second guy would like to think that they're just one less than the first guy. Okay, right? But unfortunately, the reality is this guy would be 10,000 approximately. And the third guy would be 3,300. So in general, Zipf's law says that the frequency of a word with respect to its rank falls 1 over k. And any distribution that falls 1 over k power n is called a power law distribution. We will talk about this again. Okay. So in fact, if you were to look at social networks among words, that actually explains, for example, you have power law distributions among them, and the fact that the words follow Zipf's law in most natural languages will also mean that if I were to double my corpus, I used to have 1,000 documents. I now increase it to 2,000. Or I used to have 2,000 documents, I increased it to 16,000. Okay? How much will my vocabulary increase? It turns out that the vocabulary won't increase at the same rate as the number of documents. It increases much less because the more common words will keep getting used more often. So in fact, it turns out that when we are talking about Zipf's law, there is a cousin to Zipf called Heap. Heap's law essentially says, because of Zipf's law, the rate at which the vocabulary grows with respect to the size of the corpus is sort of square root of n. And it makes sense because the more popular words are way more popular than the less popular words. Okay, so that's basically, we will look at that too towards the end of the social network discussion. But word co-occurrence patterns, other things. Okay.
Square of n not too large.
What?
Square of n not too large. Because I would expect that after some time the vocabulary just becomes standard.
I understand, but at a particular point of rise. Okay. Yes.
I have two questions. The first is that if you have pages in the graph that have no incoming links, like we were saying there are like 44 million, how could you possibly reach those pages by following the series?
Yeah, yeah. So that's a crawling. In fact, one thing that I ignored is how to do crawling. We will have to get back to it at some point of time. And normally the way you could do it, when my son is a big fan of Onion News Network. And so he makes me do these Onion News Network news stories, and I will send you one where somebody who didn't like the fact that Google can crawl their page. So Google helped them relocate. And I'll send you that link, because basically if you are anywhere, Google will find you currently. But however, they then built a little township, apparently, according to this funny news network, where there is nothing coming in, nothing going out. And so if you want to complain to Google that don't list my page, they will then relocate you to this place. So it's a good question as to if nobody is pointing to you, how do you find it? Well, where are the network, what are the IP numbers? IP numbers are 128 point something point something point something point something, right? So you can just randomly generate a string and see, is there anybody out there?
Do they do that?
In fact, that's one of the ways you actually increase the coverage.
And then my other question is, if you had...
Otherwise, there's no other way.
Yeah.
Right? So
does that root n growth apply to, for example, if I had a network of friends and each friend that I was crawling, I added as a new user to my user list. Does the number of new users increase at a square root n rate as I add new people and crawl their friends?
So you're saying whether Zipf's law and Heap's law kind of apply also to the way networks work? Actually, in fact, the bigger issue is Zipf's and Heap's law are connected to power laws. And in fact, web structure is more like a power law distribution. And if you want to develop a network that will have power law distribution, one way of doing it is something very close to what you said, which is this copy model. The way people would make a page, at least in the old days, is they'll copy their friend's page and remove some of the stuff. That basically means some of the links that their friend has, they also have. Okay, so this is also similar to rich get richer. People who are rich will get even more richer. So people who already have links pointing to them become even more popular. And that's an actual way power law distributed networks are generated. We will get to them in this class. Okay. In fact, much of what I'm doing today is really to actually explain to you that a lot of things we do here are connected to social networks, even though you may not call them that. And in fact, there are multiple ways we'll get to it. Link analysis is one. The other is, of course, this word co-occurrence patterns. The third is understanding the topology of the network, and how would such a topology actually, what is a generative model for the web topology? You can't really actually understand exactly how people are making their links. But if you have a hypothesis that this is what people are doing, and then you generated a big network which satisfies that hypothesis, and then you take the aggregate properties of this network and the true web network, and they wind up being very similar, then that means your theory is sort of kind of right. This is how science works. Right? Nobody was actually there when the evolution started. But evolution's hypotheses are essentially supported by what you see. That's the maximum you can ever get. Okay. So, and then web applications of social networks, you have web has, this is actually already, you have web pages themselves with links, you have the entire social networks which are increasing for a lot. So now the link is actually to a person, not to a page anymore. Okay? And of course there are blogs and so on. You can analyze, what can you do with them? You can analyze the influence and importance. You can talk about what are the influential pages, what are the authorities, what are the hubs, what are the pages that you go to if you feel most people are seemingly going to. That's page rank. Okay? You can discover communities. If you look at the entire web graph, and if you find that there is a small set of people who seem to have larger density of links between them than the rest of the web, then they may be a sort of a community. Okay? You can figure out what that community is. Now, the interesting thing is, if you are a DARPA or a defense person, you would hope that they are some sort of a terrorist so that you can go bomb them. If you are trying to sell a widget, you would like to see if this community is likely to be more interested in the widget you are trying to sell than something else. Okay, and so in which case you would then mass market to that community so that they'll buy your widgets. Okay, by the way, how many of you know this thing called Amway? You have friends? But Amway is an interesting network phenomenon, right? You basically get into this. It's like Costco saying you become a member of us and now you go buy some more members for us. And the more members you get, the more things you get. And at one time actually, Amway people, you will try to avoid them because they're likely to get you. They'll re-enlist you to Amway. But Amway is sort of a community. And you build a community by getting people to go and get these things. So you can discovering community on the web networks. The other interesting thing is analyzing trust. If you have lots and lots of people connected to you, you can talk about how is trust propagated. I trust this person trusts this person, maybe I should trust this person. Trust is sort of transitive, and you can actually propagate trust. And I mentioned a variant of PageRank earlier called trust rank. Okay, it actually works like that. A more interesting thing is, what do you do with distrust? I distrust this person distrusts this person. Do I distrust this third person? I trust this person, or I'm indifferent to this person? Language and proverbs in our languages are also aware of this dichotomy. An enemy of my enemy is my friend. That would mean that if you distrust X, X distrusts Y, then you actually trust Y. Okay? But if on the other hand, you're distrusting X for one reason and X is distrusting Y for a completely different reason, obviously that transitivity doesn't propagate. So distrust is harder to handle than trust. So you can all be nice and trust everybody, and so that we can write much simpler algorithms for trust propagation. Okay, but we will talk about analyzing trust and applications of trust and so on earlier, later on. And then you can also use that to sometimes handle spam, use propagated trust to fight spam. Okay, so these are some of the applications. Okay. Any questions before I move on? Yes.
In the social network, if someone has so many friends, it means it's related to the authority of that page or not? If one page has so many friends.
We'll keep to that. It turns out that there are many different ways of handling the notion of centrality. Just keep that question. Okay? That question is going to be answered in the next couple of slides. Okay, so let's start looking at social networks. Obviously, social networks are going to be some kind of graphs. Okay, so these are the entities. These can be pages, these can be people, and then there may be links between them or edges in the graph. Okay, and if so, essentially relations are edges and the entities are vertices. So you have a graph. A network is really a graph. If you have directed edges, you have a directed graph. In the case of hyperlinks, they are directed. So it's a directed graph. So relationships can be actually, they don't have to be all the same. Normally, the simplest scenario we look at is all relations are of the same type. Okay, which is like kind of, it's like I know this person kind of relation. But you could actually say, this link says I know this person, this link says I was working in the office with this person, this link might say that I went to school with this person, and so on. So there can be, edges can be different types. Okay, the simplest idea is to assume that they're all of the same type. Okay. So you have like a social network ultimately is a graph, and then you can use graph theoretic techniques to analyze the social networks. Okay. So what do you want to analyze? For example, one other issue is in terms of these networks, you can talk about the strength of ties. They don't all have to be of the same type, and they also don't have to be of the same strength. You can say some links are stronger than others. We already looked at this. In the case of local analysis of link importance, we saw if the query, if the link anchor text is not matching well with the query, then its strength will reduce. Okay? In general, you can also say, I consider this person to be my best friend. That would be like 1.0. I've kind of seen them one time when they were crossing the street. That's like 0.1 and so on. Okay? So you can, but you can also say nominal. That means you don't actually have any. There is no strength. Okay, they're all considered equal. You can consider, positive as well as negative. That means negative means they actually they kind of hate me. So I don't basically, that link then essentially says it's not a good relation that I have, but a bad relation. Okay. Okay, so graphs, and then in terms of the measures of the graphs, what do you talk about? If I show you a social network, if in terms of the measures for programs, what do you talk about? If I show you a program, the first thing, if you're a software engineer, you'll count the number of lines and say, this program is 5,000 lines of code. Okay, so obviously those are very gross syntactic measures, but that's a beginning. Okay, so some of the measures are size, which, for example, the number of nodes, the number of edges, the density, the number of ties that are present, the number of link density in the network, the out degree, which is the total number of links that are going out of any average node, the in degree, the total number of links that are coming into any average node. Okay, if they are undirected edges, then they are basically the same. There's just one thing called degree. There's no inverse of degree. Okay, a couple more terminologies. A walk is essentially a sequence of, you start from a vertex, follow the links to go to another vertex, then so on. So its walk is like a path in a graph. Okay, a geodesic distance is the shortest path between two nodes in the graph. In the social network semantics, that would be your closest connection to somebody. So I know this person because I know this person who knows this person who knows this person who knows this person. Or I also, my wife went to class, went to university with this person's girlfriend. So that's a shorter distance. So if I'm going to go to this guy and ask him to give me a job, and I'm trying to tell you, we all are from the same place, I know what's going on with you, this is a much longer story to tell than this. So I'm going to use the shorter distance. Okay? And normally between two different people, there can be multiple possible links. Okay, so geodesic distance is the shortest distance. Okay, and you can also talk about flow, maximal flow, in terms of which entities seem to be connected to more entities. Okay. Now these are all sort of obvious. So these are definitions, and these are sort of gross characterizations, aggregate characterizations, the syntactic characterizations of a network. What we really want are these kinds of measures of power and prestige in a social network. Oftentimes that's the reason you are into social networks. Okay? So how do you define the power and prestige in social network? You can talk about degree, which is the sum of connections from or to an actor. Okay, that's basically, if it's a directed graph, you would probably consider the number of back links, that is the links that are coming, that your in degree matters more than your out degree. In terms of deciding how much of a hub you are, you consider your outlinks. In deciding how much of a authority